Alright, for your notes on the video you're about to watch, I would recommend taking the grid paper space on your notes page and dividing it up into 4 quadrants. I'm going to give you some definitions on the first slide. I'd recommend doing the definitions there. And then we're going to do 3 graphing exercises. So I would say you should graph, it doesn't even look like the word graph, do the graphing exercises in the other 3 boxes and annotate them if you need to. Those are my recommendations for taking notes tonight. Here we go. In tonight's video, we're looking at position and velocity graphs. On this first slide, I've just put some definitions and short formulas that you'll need to be familiar with for the PowerPoint. So I'm going to talk through these just because I'm going to use these words and you'll need to know what they mean. Speed is a rate of change of distance, or change in distance over change in time, and it's distance divided by time, or d over t. Speed is the thing that a speedometer in a car measures. Speed is also a scalar, and that means it has nothing to do with directions. We'll get into the difference between scalars and vectors a little later, but just wanted to throw that in now. Speed is a scalar, has no direction associated with it, which means it can't actually be positive or negative. Velocity is a rate of change in displacement. It's a change in displacement over change in time. Now remember that displacement does deal with direction, and so it can be positive or negative. And then the formula for velocity, change in x over change in t, or change in displacement over change in time, which is xf minus xi over tf minus ti. Velocity is a vector, meaning it involves direction. What I'm going to do now is walk through 3 examples of changing position time graphs into velocity time graphs. So notice up here at the top there's a position time graph, the position versus time, and I'm going to take the information on it and transfer it to a velocity time graph. To get started on this, you have to know that velocity is the slope of a position time graph. So in order to take the information on the position graph and put it on the velocity graph, I have to find the slope of the position graph. Now you might notice that the position graph is going to have different slopes. The first part of the position graph, the place before where I just drew the dotted line, that has one slope, and the space after it has another slope. So I'm going to have 2 different parts to my velocity graph, because there are 2 different slopes in the position graph. So, in order to make the velocity graph, I first have to determine the slope of the first part of the position graph. So I'm just going to do a quick rise over run. I notice that we go from 0 up to 20. At the same time, on the x-axis, we go from 0 to 5. So now slope, remember, is change in y over change in x, and for the first part of this graph, the change in y was 20 meters, and the change in x was 5 seconds, which means that my slope is 4 meters per second for the first part of that position time graph. So now I just find the place on the velocity graph that would be about 4, and notice that the slope is constant. Anytime you have a diagonal line, the slope is constant on that position time graph. And so I have a constant velocity of about 4 meters per second. And then, if you remember from probably Algebra 1, the slope of a horizontal line is 0. And so for the rest of this graph, right up until the very end, I can show where that end is here, the slope is 0 meters per second, which means the velocity is constant at 0 meters per second. Also, since we just got done with dimensional analysis, note that the units for my slope match the units on the graph. Alright, and now another example. Now this graph has 1, 2, looks like 3 separate slopes. So let me do the dotted lines. I'm going to try to be really careful this time because I don't want this graph to get sloppy. So let's divide up this graph into the places as different slopes. Okay. Now, if you're wondering, how am I deciding where the graph has different slopes? Well, notice wherever the steepness of the line changes, or in this case, even reverses. Some parts it's going up, and some parts it's going down. The only time you have a constant slope is when you have a straight diagonal line or a flat horizontal line. In the case of the flat horizontal line, the slope is 0. So I've got 3 places with constant slopes, and I've got to figure out the slope on each one. Let's color code these just so we don't get confused. We'll call the first section orange. Let's do for the second section yellow. And for the third section, let's do green. Alright, let's calculate the slope of the orange section. I notice in the orange section for our change in y, we start at about negative 15, and we go up to positive 15. So that change in y would be 30. Negative 15 to positive 15 is 30. So let's go ahead and write that out. Change in y, change in x equals 30 meters. And that change happened in, looks like about 5 seconds. So my slope for the orange part of the graph is 6 meters per second. And so now I just find the place down on the velocity time graph that matches the 6 meters per second. And that slope is constant. Diagonal line has a constant slope, so it stays at 6 meters per second. Alright, now let's do it for the yellow part of the graph. I notice on the yellow part of the graph we go from positive 15 in the y down to negative 15, and we also do that in 5 seconds. Notice that change, since we went from positive to negative, is going to be a negative number, so my slope this time is negative 30 over 5 seconds, or negative 6 meters per second. And so on the velocity graph, I find negative 6. Slope is constant since it's a diagonal line. There we go. And now for the green part of the graph. I notice that we go from negative 15 up to, let's call that about, if we go with 15, it will make things easier. And also I notice that 15 happens on a grid line, so that'll make it easier. So in that place I just did, we go from 10 seconds up to 15, 16, 17, 18, 19 seconds. Okay, this one should get complicated. So let's calculate the slope. We went from negative 15 up to positive 15, so that's a change of positive 30 meters. Oh, I didn't put my units in the yellow one. Uh-oh. Units are so important. I'm going to stop and do that. So that was a 30 meters. And if you do that, I will take off a point. Dropping units, -1. Alright, and we did that change in, let's see, we went from 10 seconds up to 19, so 9 seconds. Now that's going to be a hard one. But 30 divided by 9 is close to 30 divided by 10. So 30 divided by 9 should be a little bit bigger than 10. So if I had to estimate that in my head, I might say something like 10.2. But I'm going to grab my calculator just to be absolutely certain. So let me do that real fast. 30 divided by 9 . So as I'm doing my calculator, I realized that I just said 30 divided by 9 would be 10.2. That is, of course, ridiculous. I was doing some weird mental math in my head, and I was thinking 30 divided by 10 would be about 3, and I meant to say my estimate was 3.2. So sorry about that. If I really confused you, I am very sorry. But I decided not to redo that or reverse because I think it's important to see that anybody can make a mistake, and then you realize you're wrong and you fix it. So 30 divided by 9 should be around 3 because 10 would go into 30 3 times, so it's going to be a little bit bigger than 3. So my estimate would be about 3.2, and when I do that in the calculator I get 3.333 repeating. So I'm going to say this is about 3.3 meters per second. Okay, so now I need to find the place on the velocity graph. It's close to 3. Now this pen is not fine enough to really make a distinction, so it could look like I'm drawing at 0 or at 5, but for the rest of the time on that graph we get about something like that. Alright, there we go. We just did 3 slopes of the position time and put them on the velocity graph. Alright, for this final one, I would like you to pause and try it. See what happens. Try this in that last box you should have left over if you were following my note-taking recommendation. Alright, now that you've hopefully tried it, let's do it together. So first, I'm going to divide this up into all the parts with different slopes. Remember, that's just wherever the line changes. Okay, my dotted line got a little sloppy. I'll do a little better on the next one, hopefully. It's really hard to draw this on an iPad. Okay. Ideally, I'd use a ruler, but putting a ruler on an iPad can sometimes result in wonky things happening. Alright, so I've got 4 places with different slopes. Alright, so I noticed that 2 of these places are going to be really easy, so let me go ahead and do those. I'm going to do the easy ones in purple. I think this area and this area are going to be easy because the position stays the same, and the slope of a horizontal line is 0. So, 0 and 0. Okay, now let's do the other 2 sections. We'll call those green and red. All right, for the green section, you've got to figure out the slope. Change in y, change in x. All right, I notice we go from -10 up to 20. Wow, I'm really liking the number 30 tonight. Change from -10 to 20 would be 30 meters. Notice that I'm including my units. Also notice that I included the original formula, which is something nice to do for anyone reading or grading your paper like me or an AP reader. Anyway, we did that change of 30 meters in the difference between 5 seconds and 10 seconds. So that would be 5 seconds. Simplify that, we get 6 meters per second. Alright, so I'm going to find the place that's about 6 down here. Constant slope since it's a diagonal line. There we go. Now let's do the red section. We go from +20 to 0. Now, +20 to 0 would be a negative change because we went down. So there it's going to be -20 meters. And that took, that last place isn't labeled, so I'm going to count just to be sure. That took 1, 2, 3, 4, 5 seconds. Should give us -4 meters per second. Right, find the place on the graph where that is, and boom. I have taken now 3 position time graphs and put them on velocity time graphs. It really is just that simple. The key point is to remember that velocity is the slope of position time graphs. And never forget your units. Ever. 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 The end. Good night.